So, as we were saying, the force that this water exerts on the Hoover Dam is 10 to the 11 newtons, which is 10 to the 11 newtons, and the weight of a person is roughly 10 to the 3 newtons. It's a little less than that, it's about 700 newtons. But anyway, so that's 100 million. So the force on this dam is due to this water is roughly equivalent to the weight of 100 million people. Okay, so as an engineer, you'd better make this structure strong enough to bear that load. Okay, so Newton's second law says, Newton's first law says if you don't apply a force, the velocity will be constant. So Newton's second law says, what if you apply a force? If you apply a force, the acceleration of the object is given by that. M is the mass of the object. So the acceleration of the object will be the force you've applied on it divided by the mass of the object. Now this is a vector equation, so the x component of this is equal to the x component of this vector, y component of this vector is equal to y component of this vector, and so on. The units for force are kilograms, meters per second square, and this combination of units is called a Newton in honor of Isaac Newton. Okay, so the SI unit for force is a Newton, and the British units are for force is pounds, and the unit for mass is slugs, acceleration is feet per second square. So again, like I said, this is a vector equation. The x component of this is equal to the x component of that, and so on. So the x component of the force is m times ax, y component of the force is m times ay, and z component of that. So and so you can see acceleration along an axis is caused by the net force component along that axis. Acceleration ax component of the acceleration, Fy cannot influence ax. Okay. The gravitational force and the weight. So here's the Earth. Here's an object. The Earth attracts all these objects towards its center, and that's the force of gravity of the Earth. So there's the force of gravity of the Earth on this melon. Okay, the magnitude of this force, mg, just mg, is called the weight in everyday language. All right, we need to know the normal force. You'll hear this force, the normal force, often. Okay, so let's say you're holding this laptop. This is the force of gravity on the laptop. So why isn't the laptop falling down? Well, your hand is applying an equal and opposite force. So when this object is in contact with another object, here's what happens. When a body presses against a surface, the surface deforms and pushes on the body. So your hand deformed and it pushed back on the object. And this force is perpendicular to the surface. That's why it's called a normal force. Normal meaning perpendicular. So now the two forces on the laptop are the force of gravity and your push. And these two forces cancel, and that's why the laptop is not moving. Okay, we will deal with objects sliding down inclines, so you need to know these components. Again, the force of gravity on this person is in that direction, it's straight down. Now here's the incline, that's the angle of the incline, and you see this angle is 90 degrees, so this is 90 minus theta. Okay. And you can see that from this diagram, there's the vertical, that's the vertical, this is parallel to that, so this angle is the same as this angle, so this is 90 minus theta as well. and so this angle would be theta. All right, so if this is the force, this is mg, then this is mg sine theta, which is the opposite side, mg sine theta, and this is the adjacent side, which is mg cosine theta. Anyway, so here's what you want to essentially memorize. So if you have an object on the incline, we'll represent the object by a point object. Here's the force of gravity. What we are interested in is this component of the force, which is mg sine theta, and this component of the force, which is mg cosine theta. Okay. Tension. So oftentimes you'll encounter strings that are under tension. Okay, think of them as rubber bands, and you're stretching a rubber band, and this end of the rubber band will want to pull this object in that direction. This end of the rubber band will want to pull this object in that direction. And it turns out that if these pulleys are massless, the tension will be the same on either end of the string. And so if this string is pulling this object with a force of 10 pounds, then the tension in the string is 10 pounds. That's what the tension means. So here is a pulley system. So for instance, this tension in the string is the same as long as these guys are massless. So and the idea of this pulley system is this tension plus this tension is equal to this weight, and so these tensions are half the weight of this object. Okay. Yeah. So the idea behind this is to lift this object, you have to apply a force only half the weight of this object. And of course, the price you pay is when you move 2 feet, this guy rises up only 1 feet. Okay? So even though you're applying a smaller force, you're applying it over a larger distance. And that's the idea of all machines. You're either applying smaller, most of the time you're applying smaller forces, except that you're applying them over a greater distance. Okay, so here's a cute little thing. Yeah. Now, as long as these masses are greater than this mass, so what we are saying is if m3 plus m2 is greater than m1, then the tension in this string will be m3g, and tension in this one would be m2g. Okay, so as long as m3 plus m2 is greater than m, this won't fall down. Okay, and so based on this, here's an idea. As long as the weights on these guys, you can put sand on them, and if the weights of these guys are greater than the weight of this stool, these things are not nailed to the things, and that bench won't fall down. In fact, you could sit on it, and as long as the weight of the sand is greater than your weight and that bench, then this won't fall down. We'll be dealing with springs. So here is an unstretched spring, and when you stretch the spring, to hold it there, the force you have to apply is k times x, because the spring force is minus kx. If you stretched it in a positive direction, the spring will apply a force in that direction, and if you compress the spring would apply a force in that direction. Anyway, this is known as Hooke's law. That's the force that the spring exerts when it's stretched by that amount. Newton's third law says when two objects interact, the force one exerts on the other are equal, and one exerts on the other are equal in magnitude and opposite in direction. So Here are two objects interacting. Any two objects interacting. This book will push the crate in that direction, and the crate pushes back on the book with an equal and opposite force. So there's the force on the crate by the book, and there's the force on the book by the crate. And these forces are equal and opposite, and that's Newton's third law. Now, Newton's laws are valid in frames called inertial frames of references. Inertial frames of references are frames of references that are not accelerating. So, for instance, here's since the Earth is rotating, it's spinning. The Earth is spinning. It's an accelerating frame, and it's not an inertial frame. And here's how you can see it. So, for instance, let's say you're playing ice hockey and you're at the North Pole. You hit a puck. Again, it's the puck is going on a frictionless surface, which is the ice. Okay, so if you're watching this from space, from a satellite, what you see is a puck going straight, and the Earth is spinning underneath the puck. But if you're on Earth, that is, you're attached to an accelerating frame, what you see is the puck, since it's frictionless, it actually is going straight, but it will appear to you, since you're spinning forward, it will appear to you that the puck is swinging away or turning away. And this can only happen if there's a force. So because you're attached to a non-inertial frame, you see a force where it does not exist, where one does not exist. Okay, and these are called fictitious forces. Anyway, so that was because you were not in an inertial frame of reference.